In 1969, a nuclear thermal rocket engine ran for 62 minutes on a test stand in the Nevada desert. The exhaust came out at twice the velocity of anything a chemical engine had ever produced. The engineers watching the instruments knew what it meant. One of them wrote in his notes that Mars was now a reasonable destination. The program was canceled 3 years later. 60 years on, the test stand is gone, the notes are in an archive. We are still burning kerosene. We solved the deep space propulsion problem in 1965. Then we chose not to use the answer. That choice has a cost you can measure in 90%. That is how much of a typical rocket's launch mass is propellant, meaning a vehicle that weighs 1,000 tons on the pad is delivering roughly 100 tons of everything else combined. The engine, the structure, the heat shield, the habitat, the crew, and the scientific equipment together fit inside that 10%. When you add more payload, you need more propellant to lift it. When you add more propellant, you need more propellant to move the propellant. When you need more propellant to move the propellant, that extra propellant also needs fuel. The calculation does not level out. It multiplies against you at every stage until the rocket is almost entirely tank, and the mission is a small fraction of what left the ground. That ratio does not improve as you push farther from Earth. It worsens with every additional kilometer of distance and every additional day of transit time. The equation describing this relationship was written in 1903 by a Russian schoolteacher named Konstantin Tsiolkovsky. He had never seen a rocket fly. He worked out the mathematics from first principles in a wooden schoolhouse, and the answer he produced has not changed since. To go faster, you need more propellant. More propellant weighs more. More weight requires more propellant to move it. Double the velocity you want to reach, and you do not need twice the fuel. You need far more than that, because the extra propellant needed to carry the extra fuel creates its own additional weight, which requires its own additional fuel, which adds its own additional mass to the problem. The faster you want to go, the more the calculation punishes the ambition. At the exhaust velocities that chemical reactions can produce, there is a hard ceiling on what is physically achievable without carrying a fuel fraction that leaves almost nothing behind for the mission. Starship is the ceiling made visible. SpaceX has built the most capable chemical rocket in history. It is larger, more reusable, and more cost-efficient per kilogram than anything that came before it. It has also not moved the ceiling. The exhaust velocity of the best chemical propellant available, liquid hydrogen burning with liquid oxygen, is a fixed number set by the energy stored in molecular bonds. Engineering does not change how much energy is in a hydrogen molecule. It only changes how efficiently that energy is extracted. Every refinement since the Saturn V has moved efficiency toward the theoretical maximum of what chemistry permits. That maximum is not enough to change the fundamental economics of a crewed Mars mission. Starship gets a crew to Mars in roughly 9 months. Those 9 months cost food, oxygen, water, psychological stability, bone density, and radiation exposure, all of which weigh exactly as much as the hardware needed to sustain them. The physical cost of the transit is not a Starship problem. It is a chemistry problem that no chemical rocket was ever designed to solve, because chemistry itself is the constraint. 9 months of biological maintenance consuming the majority of the mission mass budget before a single boot touches the surface. Nuclear thermal propulsion solves the specific problem that chemistry cannot address. Instead of burning propellant to produce heat, a nuclear thermal engine uses a reactor to heat the propellant directly, typically liquid hydrogen, by passing it through a superheated core running at temperatures far above what a combustion chamber can sustain. The hydrogen absorbs that heat and expands violently out the nozzle without burning at all. The exhaust velocity is roughly double what the best chemical engines achieve, because the energy available from a nuclear reaction is not limited by the chemical bonds of the propellant. That doubling does not simply cut transit time in half, it reshapes the entire mission architecture from the bottom up, because the mass that previously carried 9 months of consumables now carries 5 months of consumables instead, with a substantial portion of the saved mass converted directly into additional payload capacity. NERVA demonstrated this, not in simulation, on a test stand at full power for verified durations. Between 1959 and 1972, the Nuclear Engine for Rocket Vehicle Application program ran more than 20 engine tests at a facility in Jackass Flats, Nevada. The most advanced configurations ran at full power for sustained periods without structural failure. The specific impulse, a measurement of how efficiently a rocket uses its propellant, where a higher number directly translates into either less fuel for the same trip or more payload for the same fuel, was nearly double the best chemical engines of the same era. The engineers were not working toward a distant theoretical capability. A flight demonstration was scheduled for the late 1970s. Crewed Mars missions appeared in planning documents for the decades that followed. In 1972, the program was canceled as part of budget reductions that cut NASA's overall funding by roughly a third in the years following Apollo. No nuclear thermal engine has operated in space since that cancellation. When NASA and DARPA began rebuilding the capability under the Draco program in 2022, the team had to work from archived paper documents because the institutional memory required to reconstruct the engineering had not been maintained. A technical program that ran for 13 years, produced working hardware, and validated flight-ready performance levels had to be reconstructed from filing cabinets half a century later. The specific numbers from the NERVA program are not abstract. The most advanced NERVA-class configuration achieved a specific impulse of approximately 840 seconds, compared to roughly 450 seconds for the best liquid hydrogen and oxygen chemical engine. A Mars transit mission using NERVA-class propulsion would require a total propellant mass roughly 60% lower than a comparable chemical mission. That 60% reduction does not disappear. It converts into additional payload, more science equipment, more emergency supplies, more redundancy in the systems that keep the crew alive during the shorter transit. The difference between a 9-month transit and a 4 to 5-month transit is not just a calendar improvement. It is a radiation dose reduction that changes whether long-term Mars missions are physiologically sustainable at all. Bone density loss, muscle atrophy, and radiation accumulation all scale with transit time. Cutting the transit time substantially does not eliminate the biological damage, but it cuts it enough to change whether repeated missions are medically viable over a decade-long program. The failure that emerges from staying on the chemical ceiling is not hypothetical. A crewed Mars mission using current architecture encounters a solar particle event, a burst of high-energy radiation from the sun, during the 9-month transit. The crew retreats to a radiation shelter inside the vehicle, the smallest and most heavily shielded section of the habitat. The shelter is sized for short stays, not weeks. It draws emergency power reserves at a rate that was not planned for extended occupancy. Extended shelter use compresses the mission's total power budget, which shortens the window for surface operations when the crew finally arrives. The compressed surface window forces a triage of scientific objectives. The mission designed to answer questions about Martian subsurface geology and atmospheric chemistry returns with partial datasets from both programs because the biological cost of the transit consumed the resources that were supposed to fund the science. A robotic mission operating through the same event keeps working. Its instruments do not shelter. Its power budget carries no life support line item. It answers the questions the crewed mission was forced to abandon. 50 years of capability, stored in boxes no one kept organized. Draco, the demonstration rocket for agile cislunar operations, is the current attempt to recover what NERVA proved. Its performance targets sit in the same range NERVA achieved before the cancellation. The engineers working on it are not discovering new physics or pushing past the 1970s results, they are returning to them. A flight test is targeted in the late 2020s. If the test succeeds, it will demonstrate in space what the 1970s program was approaching when the authorization disappeared. The intervening 50 years will have produced, in terms of propulsion capability, roughly nothing beyond additional refinement of chemical rockets that already knew their limits. Nuclear propulsion in space carries a regulatory weight that chemical propulsion does not. A vehicle carrying an operating reactor must launch that reactor through the atmosphere. If the launch fails, structural breakup, range safety termination, off-trajectory abort, the reactor material returns to Earth in a dispersal pattern that is not manageable the way a fuel spill is manageable. The 1963 Partial Nuclear Test Ban Treaty, written to stop atmospheric nuclear weapons testing, created legal ambiguity around nuclear propulsion that has never been resolved cleanly for peaceful applications. Project Orion, the nuclear pulse design studied from 1958 to 1963 by a team that included Freeman Dyson, was canceled directly by that treaty, not by physics. The design used shaped nuclear charges detonated behind a large pusher plate to drive the spacecraft forward. The specific impulse was not double the best chemical engines, it was not 10 times, it was roughly 1,000 times higher, meaning a ship that carried enough pulse units could accelerate a mass the size of an ocean liner to Mars in weeks and to the outer planets in months, with enough payload capacity to make those missions scientifically and practically meaningful rather than endurance records. The team confirmed the physics. The calculations were verified. The program was canceled because the treaty written to stop atmospheric nuclear weapons testing made no distinction between a bomb and a propulsion system that used the same physical reaction for a different purpose. 1,000 times the performance of a chemical engine, canceled by a document written for an entirely different problem. Ion propulsion occupies the opposite end of the practical range. Where Orion proposed extraordinary thrust from nuclear pulses, ion engines produce thrust measured in millinewtons, roughly the sustained push of a paperclip pressing against your hand. What ion engines do instead is achieve exhaust velocities 10 to 80 times higher than chemical rockets by using electrical power to accelerate charged particles rather than a combustion reaction. The Dawn spacecraft orbited both Vesta and Ceres in the asteroid belt using ion propulsion, performing orbit changes between two different planetary bodies that no chemical mission architecture could have budgeted for. Hayabusa collected physical samples from an asteroid surface and returned them to Earth across billions of kilometers, with ion engines handling the long cruise phases. Neither of those missions would have existed in the form they took without ion propulsion. Neither of them carried a crew, and neither of them could have. The acceleration timescale of an ion engine, months to build up useful interplanetary velocity, is incompatible with a crewed mission that cannot afford to spend 6 months in deep space simply reaching operational speed, exposed to radiation the whole time with no shelter yet constructed at the destination. The tool that does extraordinary work for probes is the wrong tool for people who need to arrive before their food supply runs out. Laser propulsion removes the propellant problem and replaces it with an infrastructure problem that has not yet been built. A solar sail accelerates a spacecraft using light pressure, photons pushing against a large, thin surface with no onboard propellant consumed. Ikaros, a Japanese spacecraft launched in 2010, demonstrated solar sail propulsion on an interplanetary trajectory for the first time and confirmed the thrust was physically real. The Breakthrough Starshot initiative takes this concept to its theoretical edge. A ground-based laser array producing focused power at gigawatt scale, aimed at a meter-scale sail carrying a gram-scale probe, accelerating it to 20% the speed of light over a short burn. A probe moving at that fraction of light speed reaches the nearest star system in approximately 20 years. The physics underlying the concept have been reviewed by serious researchers and are not disputed. The laser array required to execute it does not exist at any scale approaching what Starshot describes, has never been prototyped in any meaningful fraction of its required output, and would cost more than any single space program in history to construct and operate. Breakthrough Starshot is not speculative science. It is verified physics waiting for a commitment that is civilizational in scale rather than programmatic. Every alternative to the chemical ceiling is waiting for a decision, not a discovery. The physics were discovered decades ago. The mission architectures currently in development for crewed Mars transit cite nuclear thermal propulsion as a component of later phases. Those citations are not wrong about the physics. They are making an assumption about institutional continuity that the historical record does not support. NERVA was approaching flight readiness. The decision not to fly it was made by budget committees responding to post-Apollo political pressure, not by engineers examining performance data. Draco, however competent and however funded, is a demonstration program. Between a successful demonstration and an authorized flight program lies exactly the same decision space that closed on NERVA in 1972. That space has not changed shape, and the regulatory framework that complicated nuclear propulsion in 1963 has not been updated to reflect 60 years of peaceful application proposals. The ceiling is not chemistry. The ceiling is the distance between what engineering has proven and what institutions have been willing to authorize, and that distance has outlasted every crewed Mars proposal ever written. NASA's current Moon-to-Mars architecture, which targets crewed lunar surface missions in the late 2020s as a precursor to eventual Mars transit, has not committed to nuclear thermal propulsion for the Mars transit phase. The program that would demonstrate the technology is a separate line item, funded separately on a schedule that assumes no political disruption between now and the end of the decade. If Draco flies on schedule and performs as expected, the decision whether to build a flight program around its results will be made by the same kind of institutional process that canceled NERVA when the results were already on the table. The propulsion problem has a known solution. It has had one since before most of the people currently writing the mission plans. The answer is in the archive. The test stand is gone. We are still deciding whether to build a new one.